Hello, and welcome to this really unique opportunity for a virtual building tour. We are standing on the balcony of the mechanical room at what is called the Southwest Chiller Plant on the University of Utah campus. The campus has 3 chill water plants. This is their biggest one, and I'd like to extend a big thanks to them for opening their doors to us and letting us spend time in the plant so that we can learn about it, we can see the equipment, we can see the instrumentation. It's a really unique opportunity. Plus, you can actually hear me because we're not in the chill water plant where it's super noisy. So before we start walking around and touring the plant, I want to do a quick conversation about how a chiller works, and then a little bit of background and refresher probably on how buildings use energy and why are we spending time in this mechanical room off in the corner of the campus when there are all these big buildings around. So we'll talk a little bit about why we're focusing our efforts in this particular space. So here's a schematic, really simple schematic of a chill water plant, and it's exactly what we see. When we go walk around, you'll see all these pieces of equipment, but what I want to show you is how a chiller works. It's basically got 4 components: a condenser, a valve, evaporator, and a compressor. And there is refrigerant. This is the refrigerant circuit in a chiller, and that's how it provides cooling. This is exactly like the refrigerant circuit you have in your air conditioning unit at your house. You have a condenser, a valve, evaporator, and a compressor. These 2 pieces of equipment sit outside, and the evaporator and valve is within your air distribution, or as a coil in your furnace. So the refrigerant circuit behaves in exactly the same way. The difference is this piece of equipment is probably 4,000 times bigger than your air conditioning unit in your house. And the other difference is that we're making cold water instead of making cold air. And we make cold water so that we can pump it in a distribution type fashion out to the buildings on campus. Even in a single building, a lot of times a chiller will be in the basement and it's pumping water to air handling units on multiple floors throughout a single building. So chillers are a really common way of addressing large spaces that need a lot of cooling, because water is an efficient way of delivering that cooling. So when we talk about the chill water, we're talking about this water is probably 42 degrees that's being pumped out to the buildings. And then the other water loop is a condenser water loop. So when your air conditioner at your house is condenser air cooled, that's the thing that sits in your backyard. But the more efficient way to do it is with water. So we call this a condenser water loop. There's a pump that pumps the water through the condenser bundle of the chiller. It goes out to the cooling tower, and that's actually where we're going to start on this tour, is outside at the cooling tower, where it trickles down through fills, captured in a basin, and then continues to loop around. So that's a quick schematic of a chill water plant. Let's move on a little bit to how buildings use energy and give this a little bit more framework in terms of why, as engineers or energy managers, we're focusing on this particular kind of plant. So this may be a refresher for you. You might have seen this end use breakdown before, but what this shows us is by BTU, how buildings use energy. And if we start with a big piece of pie, we can see that space heating, not surprising, is the biggest energy user by BTU in a building. And this is considering all types of buildings in the continental US. So space heating is our biggest energy user, a little bit of domestic hot water, and then I'm going to pop back up here to this other side and work our way down. Fans and pumps, 16% of energy use. Space cooling, that's exactly what we've been talking about, is 12%. Lights are also 12%. And then this final piece of pie is called internal equipment, and that is anything you see plugged into the wall. So that, from a building user's perspective, that is the energy use that you see. So the lamp on your desk, the printer in the hallway, the coffee maker, anything you plug into the wall is considered internal equipment. So as a building occupant, you tend to think that the only thing in your building using energy is your lamp and all the things that you see. But actually, all of this HVAC equipment behind the scenes is really the biggest energy user in the building. Now, the other interesting thing about that is if we break this pie apart and we look at the right side of the pie, your space heating is typically supplied by natural gas. And on the left side of the pie is typically supplied by electric. And what's significant about that is that electric by BTU costs you about 3 times what natural gas costs you per BTU. So this left side of the pie is costing you 3 times what the right side of the pie is costing. So that causes us to focus more on fans, pumps, space cooling, lights, and internal equipment. So if we reframe this piece of pie to a cost visual, it looks like this. And now all of a sudden, space cooling and fans and pumps are 40% of the utility cost in a building. So what does that mean? At the university, they spend $7.5 million a year in gas and $17.2 million in electric. Now, I believe those are 2018 numbers. The other cool thing about that, if I may tout their successes for a minute, is those numbers are the lowest the utility spend has ever been on campus since 2011. And that's despite campus growth of 23%. So when you talk about this unique opportunity to tour a really big energy user plant, this is on a campus that has really had great success at reducing their energy use. So with that background, let's go walk into the plant. I want to give you a little idea of where we are. We are in Salt Lake City, which is in the Intermountain West. We are just west of the Rocky Mountains. We also have mountains in the backyard. And this is the University of Utah campus. You can see it's right at the base of the foothills. The campus is about 1,500 acres. There's 32,000 students at this campus. That includes undergrad and graduate students, just to give you some idea of the size of the campus. And the building we're going to go to is the one that says Utah on the roof. And this building is the old field house. We'll look at it a little bit closer here in a second. What's cool, it's right across from the stadium. So this is a little bit of the athletic center at one time, but they've now turned that into the chilled water plant. And it's providing cooling to all of the buildings in this blue block, which is at least a third of the campus. It's about 2 million square feet of building that this is providing cooling to. So if we zoom into that a little bit more, here's our field house. The chillers are located on the east end of the field house. And if you recall from our central plant schematic, one of the important pieces of equipment is a cooling tower, and that's what's sitting right outside. So these 2 circles are the fans on the top of the 2-cell cooling tower. And those fans are blowing air upward and drawing air through these little side panels, and we'll get a chance to walk around. But the central plant is providing cooling to all of the buildings. This is almost the way the chilled water pipe loop runs. This is a brand new law building. It's providing cooling to the chemistry building where all the student laboratories are. There's a biology building. The Marriott Library is probably one of the biggest buildings on campus. So all of these buildings in this picture are being cooled by the plant that we're going to go walk through. So with that background, let's go down to Earth and have a look around. So this is the cooling tower. And you can see the 2, very subtly, the tops of the fans on the cooling tower. They're giant. Of the field house, and you can see it's a really cool building. Not all central plants have this kind of cool building, but this used to be the place you would go lift weights if you went to the university in the 90s. And so before we even go inside, there's this interesting piece of instrumentation already that's really relevant to the control of the plant. And so when I took this photo, I sent it to the central plant operator, and I wanted to make sure that it is in fact the outside air sensor. That's why I said, Steve, is this the outside air sensor via email? And he wrote back and he said, let me know if it senses that there's no outside air. So it's really the outside air temperature sensor, but confirmed, this is the outside air temperature sensor. So this is one of the really key pieces of instrumentation in terms of controlling the plant, and overall influences many of the control devices that the building automation system controls. And that's me. It was quite early in the morning and very sunny on this side of the building. So let's walk around the cooling tower. So now we're on the other side of the building. This is the cooling tower that we've talked about many times. The chillers are inside this building. Air for the cooling tower is going in this fill area and out the top fans that we saw. If we go a little closer, this is the piping being pumped from the plant. That cooling tower cell is running, as you can tell. I asked him if we could go inside the cooling tower, and he said no, but you can go on the roof. So I'm sorry to disappoint you, but I did not go up that ladder to the roof of the cooling tower. But there's already some control devices that are relevant to the operation of the plant. What we see here is a valve. This is a valve wafer. It's called a butterfly valve in between these two flanges. So in the pipe, there's a wafer that can shut off water and let water flow. This device is the actuator that's getting its signal from the building automation system that tells it what position to be in. And then you can see it's mechanically linked to the valve in this other pipe that's bypassing the tower. So this actuator is getting a signal to tell the water whether to go to the top of the tower or actually bypass the tower, and that is contingent on often outside air temperature so that they don't freeze the tower. So already we can see that instrumentation is informing control devices. So now we've stepped inside and we're looking at chiller number 1. That's chiller 1. Tightly tethered over chiller number 2. And then the chiller piping is traversing the entire length of the chemical. The pumps on the bottom, there are 2 water pumps on the water chiller. The pumps on the top, on the balcony, are the pumps that pump the water out to the building. Now, if you had a hard time hearing me while we were actually in the plant there, that's authentic. And when you walk around in a chill water plant, you usually get about 80% of what the facility guy is telling you. So that was an authentic experience. But we'll take a look at each one of these things a little closer. These are the pumps that are pumping water to the building. So the water is coming out of the chillers through the pump up the top, and it runs in this giant header in the back. This big pipe goes out to the west, and this big pipe goes out to the east. These are probably 24-inch pipes, pretty huge. So over at the chiller, this is a Trane chiller. It has 2 compressors, so they kind of call it circuit 1 and circuit 2. This is the only chiller that was running, and only circuit 2 was running while we were there. And what I thought was kind of cool about this, I asked the operator to toggle through this control panel, because you can obviously see more information that we know how to digest about the chiller operation right on the chiller control panel. But what I thought was cool was that we can read power. So right here, it's telling us that this compressor that's running is drawing 84 kW. So what does that mean? Is that a lot? Is that a little? It's only 84. 84 kW. I did a little back of the napkin sort of fake calculation. If we assume that this chiller was running for half of the year, so May through October, so let's assume this chiller is running May through October at this rate, which we know the chiller is going to modulate as temperatures become hotter. It's going to run at way more than 84 kW, and circuit number 2 is going to come on. Actually, the other chiller is going to come on. But if this ran at 84 kW for 6 months, it would cost you $29,000. So that gives you some idea why we're paying such specific and careful attention to the way the chillers are controlled and the pumping system is controlled so that it can be run as efficiently as possible. So the other big energy user in the plant are the pumps. These are the pumps that pump water to the building. They're 250 horsepower. I didn't actually get a video of these, but I got a quick little video of the pumps downstairs. So what's happening here, these are pumps to the chiller. Water down the pipe pump out right here. Motor. Motor's one to go first. And motor 100 horsepower. So that's pretty giant for an HVAC motor to be 100 horsepower. So this is the pump that we just looked at. This is our 100 horsepower motor. These guys upstairs are 150 horsepower, I think. But what I want to show you in this picture is that these devices over here in the corner are called variable frequency drives. And this is the electrical piece of equipment that's actually controlling the speed of these pumps. And a variable frequency drive, you'll hear it called a VFD. You might also hear it called a VSD, variable speed drive, essentially the same thing, controlling the speed of the pump. And if we control the speed of the pump, then we're meeting load and we're reducing energy use on the whole system. If we look a little closer at this panel, you can often toggle through these menus and get to kW. At this point, the operator had left me alone in the plant and I chose not to press buttons on the VFD. But what we can see here is that this is running at 31 Hertz and full speed would be 60 Hertz. So the pump's running basically at half speed. What's really impactful about slowing down the speed of the pump is, if you remember from your engineering classes, the affinity laws, if you slow the speed of the pump, you save power to the cube. So there's a really great benefit in peeling off even like 10% speed off the pump. Sometimes we look to go to 90% speed, 85% speed, because then you're saving power to the cube by that simple speed reduction. So it's really quite impactful. And a variable frequency drive is how you accomplish that. So here's the tag on this one, VFD2, pump 2. Another important thing you'll see in the field seems really simple compared to all of that complicated control panel. But this is called a HOA switch, hand off auto. And anytime you have a pump or a fan, you will see an HOA switch in the field. And auto means that's a good thing. Auto means that this pump or fan are getting their control signal from the building automation system. And we didn't really talk about the building automation system too much yet, but all of this equipment that we see is being controlled by a computer. And that computer is called the building automation system. The BAS, every industry has its acronyms. So the BAS receives signals from temperature sensors and flow meters, which we'll see. And then via the programming, it commands the pumps and the chillers and the staging of equipment to respond to that load. So when a piece of equipment is in auto, it's actually getting that commanded signal from the building automation system and will slow down accordingly. So that pump we saw running at 31 Hertz had gotten its signal from the building automation system, because this is an auto. If this is an off, then the equipment is simply commanded off right there in the field. And if it's in hand, that means it's running full speed. And a lot of times this is used when facility staff are doing work on the piece of equipment or doing maintenance. Sometimes they want to turn it off, or they want to run it in hand to see how it's performing. And then sometimes they forget to put it back to auto. So go look at your HOA switches. Make sure they're always in auto. That means you're actually running optimized according to the building automation system. I always have to proselytize about the HOA switch. Auto. Okay, so to close out our story on pumps, if you remember from our chilled water schematic, we had chilled water pumps, and then we had condenser water pumps. These in the picture are condenser water pumps. What's really unique about these is they're called vertical turbine pumps. It's actually kind of cool that you guys get to see these. They're not super common. But the way this works is we are standing on top of the cooling tower water basin. So there is a sump underneath us, underneath this concrete. That plate, you could probably stick your head down in there and see the water level. But we're standing on the pool of cooling tower water or condenser water. And these pumps have a shaft and impeller that's immersed in that water and draws it up through this pipe and pumps the water into the chiller and then back to the tower. So again, this is the condenser water loop. In this case, this particular pump was running, and I'll direct you to the electrical equipment in the back, and you might be able to guess that this is the VFD. So this is the variable frequency drive for each one of these pumps. So these are the condenser water pumps, again, that are pumping water through the condenser bundle of the chiller and then out to the cooling tower that we saw outside. These are essentially what's making the waterfall outside. And then finally the chiller itself. So let's go have a look at this thing. These are giant. That is circuit number 1. Up on the top. I am not tall, and these are giant. And if we look at those kind of from above, this is the condenser bundle. So this is what's getting the water from the cooling tower. The evaporator bundle is underneath all this equipment in the back, but it basically has the same round kind of end cap. It's a shell and tube heat exchanger, basically. And then this is a compressor where the refrigerant is compressed, so it comes out of this centrifugal compressor into the condenser to turn back into liquid. So that's a 2,000-ton, 2-circuit chiller that's water cooled. Pretty cool, huh? And then I want to tell you about one more piece of equipment that is an energy efficiency piece of equipment. And on the way to getting to that equipment, I'll show you another set of valves. This is on the condenser water, as it says. This is never trust pipe labels. There are occasions where the arrows are going the wrong direction and you scratch your head at the plant for like hours and they're like, oh, that label's wrong. But in this case, these are all actually right. But again, you probably know there's a valve inside here and there's a valve inside this flanged disc, and it's being actuated by this actuator that's getting a signal. You can see the electric signal from the building automation system. And it's saying this line should be closed and this line should be open. And what we're looking at here is a condenser water. This one goes to the chiller, just like the circuit that we've talked about. Cooling tower water, condenser water goes to the chiller. But in certain cold conditions outside, a lot of times the cooling tower can make cold water, and we can simply exchange that cold water from the cooling tower and make chilled water out of that. And in those cases, this valve switches, sends condenser water through this pipe, and condenser water supply, that's a strainer, that's cleaning it up, into this as a heat exchanger. So this is called a plate and frame heat exchanger. These, I'll show you a close-up picture in a second, but these are little tiny plates very close to each other. And condenser water flows on one side and chill water flows on the other side. So you can see a set of pipes coming out the back behind, and that's the chilled water side. So basically what we're doing is taking water from the cooling tower and making cold chilled water, and that means, what does that mean? You don't have to run the chiller. So when we saw 84 kW on the chiller, like it'd be nice not to have to pay for that 84 kW, right? If we can just exchange water right here in the plate and frame heat exchanger, then we basically have what we call it free cooling. You'll also hear this called water side economizer. Water side economizer, plate and frame, those are kind of the common terms for this kind of energy efficiency option in a chill water plant. And this is the up close. So you can see how these plates of metal are super close to each other. Millimeters of opening that the water runs through to exchange condenser water and chill water. Okay, so that's pretty much all the equipment. And so what is this all about? This is the building automation system graphics. So if we were to log into the computer that controls all of this equipment, this is what we would see. It would be a lot more dynamic. There's like kind of visuals on these kinds of software programs that show you when things are running. So for example, over here at the cooling tower, we've got the little water spraying. And if you remember when we stood out there at the cooling tower this morning, we could hear one of them running. The other cooling tower was off because we're only running one chiller. So the other thing we saw out at the cooling tower was this three-way valve. Remember the very first brown pipe that we saw? So that valve was either sending water up through the fill, or it can bypass if it's really cold outside. And the water comes back into the plant, and then this is the sump that we were standing on top of that had the concrete and the really big vertical turbine pumps. So these pumps look like these really little dinky things, but in fact they're giant. Like I think these pumps are 250 horsepower. They're huge. One of the pumps in the plant I saw nameplate was 250 horsepower. So there's a lot of horsepower going on here. So those pumps are pumping water into the condenser side of the chiller. And then it simply goes back out to the cooling tower. That's it. So, but you're like, wait, what about free cooling? So the pumps do have the option to send water. There's our three-way valve over to the plate and frame heat exchanger. So you can see that all of the physical equipment that we're seeing is being commanded by this computer software. And the computer software is also receiving signals for temperature, for example. There's a little T temperature sensor in this pipe that's reading 55.9 degrees. And there's temperature sensors all over the place so that the programming can understand how the plant is performing and what the buildings need, and then sequence the equipment to meet that load in an efficient fashion. So again, this is the building automation system. It shows all the information that's coming in and the commands that are going out to control the equipment. So that's condenser water side. Oh, and here's our outside air sensor. Yes, there is outside air, and yes, the outside air also has a temperature of 61.2 degrees. So this screenshot was exactly taken on the day I was out there. I was out there pretty early in the morning. I think this was taken about 11 a.m. But all of the equipment aligns with what we really saw in the field. There's only one chiller on. This chiller's off. You can see that the valves to the chiller that's off are closed. The valves to the chiller that's on are open. And this graphic is just for condenser water. And I'm going to scroll down, I'll show you the graphic for chilled water. and we don't have to go through that in great detail, but I want you to understand like how much instrumentation and feedback goes into controlling these really big pieces of equipment. So again, this is chilled water. Here's the chiller that's operating, and we only saw one circuit running. So here's circuit 1, actually that's circuit 2 is operating. Circuit 1 is off according to the building automation system. The valves to that chiller are open. We're making 42.8 degree water, and it's coming back at 45.7. The other cool thing I want to show you on here, you're like, why is there a big white space? They intend to install chillers for a future expansion of this plant. They thought they would need 2 more, but actually the plant's running efficient enough. They think they can really only just install 1 more chiller, do their expansion, and still have enough redundancy. So that's why the white space. The other thing I can show you here is the heat exchanger. So if we skip the chiller, the water goes through the heat exchanger, gets cooled from cooling tower water. And then these are the pumps. These are the pumps that are downstairs, circulating water through the chiller. These are the pumps that are upstairs, sending it out to the building. And I'm super bummed this is cut off. It makes me want to scroll down in our slideshow to show you the piping going to the building, but it's actually got cut off on the screenshot. But you get the feeling for exactly the exact equipment in the plan is fully represented in the building automation system. And then the final thing I want to show you here is a BTU measurement. So there's a temperature sensor here, connected to, this is a flow meter. This is measuring water flow in the pipe. So 4,408 gallons per minute is being pumped through this pipe and measured right here by this device. And then this is another temperature sensor. So this is essentially like supply and return temperature readings with a flow measurement. So from a temperature differential and a flow, you can calculate BTU. And I'll show you what that instrumentation looks like in the field. It's kind of cool. So here we are. This is the east side piping. So this chill water line is going down into the ground, and these are basically buried. They're kind of direct buried. They're not in a tunnel. They're direct buried to make that giant loop around campus that we talked about. So this is the pipe going out, and then this is the water coming back from the giant loop around campus. So supply and return. And this is the flow meter. So when we looked at that device, it was measuring gallons per minute. That's what this device right here is doing. This meter is inserted into the flow, and it is sending its signal electronically back to the building automation system. And you're like, well, wait, what about those little red dotted lines that went to temperatures? So if we go downstairs, come with me. If we go downstairs, now we're in the same pipes, chill water supply, chill water return, and here's our temperature sensors that are both sending their signal back to the building automation system. So there's a insertion probe into the water flow of the pipe that reads the temperature. And from that, we can calculate BTU. And the BTU is calculated in a meter right there in the field. This is BTU meter 3 secondary chill water. So this is one secondary chill water means it's the water that's being pumped out to the building. So 10,000 BTUs is being measured right now via that instrumentation. And to kind of give you a bigger picture of how does all this control communication work, this little meter right here, that's the BTU meter we just saw. There's a BTU meter going to the east side piping, a BTU meter on the west side piping, and then a BTU meter on the primary loop, which is just the loop of water within the plant that's being circulated through the chillers. And then all these other panels are receiving all of those signals that we have talked about and controlling all of the devices in the plant. So if we zoom into one of those panels, and we open it up, this is what we see. So there's just a series of terminal strips that are analog inputs, analog outputs, digital inputs, and digital outputs. And looking a little bit closer, you can see these are literally just the control wiring from every device in the plant that's coming into this terminal strip. And this is what's informing those graphics that we saw. And then just another couple up close. This is the chill water return temperature. That's simply a temperature sensor inserted in the pipe and sending its signal back to the control panel that we saw. And you often see these concurrent with a real-life thermometer. So when you're actually standing in the plant, you can say, okay, the chill water is 42 degrees. And then we see the same thing on the heat exchanger. Hot side water, so this is heat exchanger 1, condenser water supply temperature. And then they often give you a pressure gauge so that you can see what the pressure drop is across a device, which is an indication of how that device is performing. Also, it can tell whether or not pumps are running and what speed they're running at. And then a thermometer so that you can do your analysis in the field. So that's the instrumentation is fairly simple and robust enough to control one of the biggest energy users on campus. And you just got to see all of it. So that kind of ends our conversation around the water side. This slide is blank on purpose. I want to pivot a little bit to air side. So we've been in the plant, we understand what the chiller does, we understand what the pumps do, and we're sending chilled water out to the campus. So what's it doing out there? What does that look like? And I wasn't able to get in any of the other buildings on campus. They are pretty much on lockdown. But in the plant, there was an air handling unit cooling the plant. And it wasn't on right now, but I can show you what it looks like. Basically, as this chill water pipe is being distributed around campus and into a building, it branches off, and then it supplies an air handling unit coil. And that's what we can see right here, these two pipes. This is chill water supply and chill water return. At the back of chill water return, chill water supply being this air handling unit. So inside the air handler water coil, pull valve, making cold air, blowing it into the plant. So this device is really quite simple. Air handling units in buildings can be as big as a room. You can often enter them and they're twice as tall as you are. So this is a really small visual of how the chilled water is getting used out in buildings. But I've got one last kind of graphic screen. And again, this is from the building automation systems. You can see everything about how the equipment's performing. So what we just saw is the fan. This is a heating coil. And there's a chill water piping. And the valve's closed. That's the valve that we just saw. And there's a discharge air temperature sensor reading. The unit isn't actually on, but you can see the points of communication that go back to the building automation system. And there's our outside air temperature. It changed by like 0.2 degrees in between screenshots. And that's it. That ends our building tour of the Southwest Chiller Plant. And again, it's 4,000 tons of installed cooling, 2,000-ton chillers, really quite huge, with an understanding of the equipment and instrumentation that controls it all. So again, appreciation to the University of Utah for opening their doors for the making of this film. My name is Jane Geyer. I'm a mechanical engineer, and I'm glad to be able to share this information with you. My contact information is included. If you have questions, I would really welcome them. Thank you all.